Good morning, dear students. We know that two-dimensional problems are modeled as plane stress case and plane strain case. In previous class, we discussed about the plane stress case or plane state of stress. We can say two-dimensional state of stress. Now we shall see plane strain case, or we can say two-dimensional state of strain, or we can say plane state of strain. For plane state of strain, in-plane strains are non-zero. In-plane strains are non-zero. Now we shall see what are the in-plane strains. The in-plane strains are epsilon xx, epsilon yy and gamma xy. In-plane strains are non-zero. Therefore, epsilon xx is not equal to 0. Epsilon yy is not equal to 0. And gamma xy is not equal to 0. And moreover, epsilon zz equals to 0. Or you can say epsilon z. Gamma yz equals to 0. And gamma zx equals to 0. Finally, sigma zz is not equal to 0. Very, very important. Sigma zz is not equal to 0. Sigma zz is not equal to 0. Understand this. For plane state of strain, sigma zz is not equal to 0. Hence, I take the expression for sigma zz or sigma z from the stress strain relations of three-dimensional state of stress. How you get sigma z equals to E by 1 plus nu into 1 minus 2 nu into epsilon x plus nu into epsilon y plus 1 minus nu into epsilon z. For plane state of strain, sigma zz is not equal to 0. Why it is not equal to 0, that we see here. Because epsilon zz equals to 0, put this epsilon z equal to 0. Then what you get? Sigma zz or sigma z equals to E nu by 1 plus nu into 1 minus 2 nu into epsilon x plus epsilon y. Nu comes out because here, so nu is there inside. Epsilon x is multiplied by nu and epsilon y is multiplied by nu. Therefore, nu comes out. This is the reason why here, within the brackets we see epsilon x plus epsilon y. This is the expression for sigma z. So, sigma z is non-zero. That is what we have written here. Understand? Right. Now, for two-dimensional state of strain, we get the stress-strain relations like this. I told you in the previous class, for two-dimensional state of strain, we get the stress-strain relations like this. A matrix sigma of size 3 by 1 equals to a matrix D of size 3 by 3 into a matrix epsilon of size 3 by 1. Okay. This is a column matrix of size 3 by 1. What are the elements of it? Sigma x, sigma y, tau x. And matrix D is the material matrix. And matrix epsilon is a column matrix of size 3 by 1. What are its elements? Epsilon x, epsilon y, gamma xy. Right? Now the size of this matrix D is 3 by 3. How do we get? We get the expressions for sigma x, sigma y and tau xy. How do you get the expression for sigma x? From the stress-strain relations of three-dimensional state of stress, we get sigma x or sigma xx equals to E by 1 plus nu into 1 minus 2 nu into 1 minus nu into epsilon x plus nu into epsilon y plus nu into epsilon z. This is how we get the expression for sigma x from stress-strain relations of three-dimensional state of stress. But what we are discussing here, the plane state of strain for which epsilon z equals to 0. This is the reason why. So how you get E by 1 plus nu into 1 minus 2 nu into 1 minus nu into epsilon x plus nu into epsilon y. This is how we get expression for sigma x. Right? Now one expression we have. Another expression that is for sigma y. So what you get? Sigma y which equals to E by 1 plus nu into 1 minus 2 nu into epsilon x plus 1 minus nu into epsilon y plus nu into epsilon z. But for plane state of strain, epsilon z equals to 0. Therefore, so what you get here? You get sigma y equals to E by 1 plus nu into 1 minus 2 nu into epsilon x plus 1 minus nu into epsilon y. This is how you get. This is the expression for sigma x and this is the expression for sigma y. For plane state of strain or for plane strain case. Right? And what is the third one? We know that within the limit of proportionality according to Hooke's law, shear stress by shear strain tau xy by gamma xy equals to shear modulus of the G. Okay? We also know that E equals to 2G into 1 plus nu. Therefore, you can replace this G and modify the equation. Right? And you can express the stress-strain relations in matrix form for plane state of strain. This is for sigma x, this is for sigma y, and you get the expression, for tau xy from this replacing this G using equation E equals to 2G into 1 plus nu. Okay? Now, see here. So this matrix has the elements sigma x, sigma y, tau xy. E by 1 plus nu into 1 minus 2 nu, it comes out. Right? Now, so here this is the matrix having the elements epsilon x, epsilon y and gamma xy. Now, this matrix contains in first row 1 minus nu, 0. Next nu, 1 minus nu, 0. Next 0, 0, 0.5 minus nu. This is how you get for plane state of strain. These are the expressions for plane state of strain. Okay. So far we have discussed about the two-dimensional state of stress and this two-dimensional state of strain. Now, we see an example for plane strain case. So here we have a long cylinder. It is subjected to internal pressure P. It acts as the transverse loading. Okay. Now, if you consider an element with small thickness, the strain in the direction of its length is 0. So this is the example for the plane state of strain. A small thickness in the loaded area of a long body of uniform cross section subjected to transverse loading, that is internal pressure. Right? Is the example for the plane state of strain. Now, von Mises stress. We learned the theories of failure in the lower classes. Von Mises theory of failure. What it says? According to this theory, the energy due to distortion is responsible for failure of the material. Energy due to distortion is responsible for failure of the material. That is what von Mises theory of failure states. Now, when the failure takes place, when the von Mises stress is greater than or equal to stress at yield point. When the von Mises stress is greater than or equal to stress at yield point, failure takes place. If the von Mises stress is less than or equal to the stresses yield point, failure does not occur in the structural component or machine component. This is what von Mises theory of failure states. Now, we know that according to the von Mises theory, sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square equals to 2 sigma y square. 2 sigma y square. What is sigma 1? It is the principal stress, maximum principal stress. Right? Why I say maximum principal stress, that we see. And sigma 2, sigma 3. They are also the principal stresses. Sigma 1, sigma 2 and sigma 3 are the principal stresses which we consider for triaxial stress state. Triaxial stress state. Example for triaxial stress state. You take a body which is in the form of say sphere. Assume that it is made of metal. If you immerse this body in a reservoir containing fluid at rest, the surface of this body is under hydrostatic pressure. At every point, the pressure acting on the surface of this body is normal to the surface at the same point. And moreover, the intensity of the hydrostatic pressure at every point on the surface of the body is also same according to Pascal's law. This case we can consider as a body under three-dimensional loading. Therefore, it is a three-dimensional problem. For such a problem, you can determine three principal stresses. What are they? Sigma 1, sigma 2, sigma 3. Which one is maximum? Which one is minimum? A question comes into mind. Now, I assume that sigma 1 is greater than sigma 2, which is greater than sigma 3. This is how I take. Right? Now, which one is minimum? According to this condition, sigma 3 is minimum. Right? Which may not happen all the times. Sigma 2 may be minimum. Sigma 2 may be minimum. If sigma 1 and sigma 2 are equal, for example, sigma 1 is positive and sigma 2 is negative, and sigma 3 lies in between sigma 1 and sigma 2, then sigma 2 becomes minimum. Once again I tell you, say sigma 1, is equal to sigma 2. But sigma 1 is positive and sigma 2 is negative, and sigma 3 equals to 0. In this case, which one is minimum? Sigma 2 is minimum. Now, how we arrange these three principal stresses? Sigma 1 is greater than sigma 3, which is greater than sigma 2. In this case, sigma 2 is minimum. Therefore, this is not the essential condition. Sigma 1 greater than sigma 2 greater than sigma 3, it is not the essential condition. Right? If I assume that sigma 1 is greater than sigma 2, which is greater than sigma 3, okay? In terms of these three principal stresses, according to von Mises theory of failure, we get an expression like this. This we had learned in lower classes. Right? Sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square equals to 2 sigma y square. What is sigma y? Stress at yield point. Sigma y is stress at yield point. So this is the equation which we can use for three-dimensional problem. Okay? Now how do you determine the von Mises stress? The von Mises stress you can determine. I told you that failure takes place if von Mises stress is greater than or equal to stress at yield point. If von Mises stress is less than or equal to sigma y, failure does not take place. That is what I said. This is the reason why. What I do is, I take this 2 to the left hand side. Therefore, this by 2 you get equals to sigma y square. Then you determine sigma y. Sigma y, what you get here? So this by 2 under root you get square root of this by 2 you get for sigma y. So that is the reason why the LHS I define this as von Mises stress. Okay? Square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square by 2. That is the von Mises stress. Then how you write? After simplifying, von Mises stress equals to 1 by root 2 into square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. This is how you can define the von Mises stress. If this von Mises stress is greater than or equal to stress at yield point, failure takes place. This is more suitable for ductile materials, and this theory of failure supports the case where a body is under hydrostatic pressure. The body under hydrostatic pressure. I said no. When you take a body made of, say, metal and immerse it in a reservoir containing fluid at rest, the hydrostatic pressure acts on the surface of the body at every point. The intensity of pressure is same at every point according to Pascal's law. Understand? Now, if sigma 1, sigma 2 and sigma 3 are the principal stresses, how you write the, how you represent the matrix? So like this. You can represent like this. You know how to represent, the 6 independent stress components in matrix form. This we have discussed in one of the previous classes for 3-dimensional state of stress. For 3-dimensional state of stress, we represented the stress matrix like this. The first row of the elements are sigma xx, tau xy, and tau x. First row of the elements for 3-dimensional state of stress. And for second row of elements, tau yx, sigma yy, and tau yz. Now the third row of elements are tau zx, tau zy, and sigma. So here tau xy and tau yx, they are equal to each other because I told you shear stresses are crossed because tau xy equals to tau x. Similarly, tau xz and tau zx are same. Hence, tau xz equals to tau zx. Shear stresses are crossed. Next, tau yz and tau zy are same because shear stresses are complementary Therefore, all the 9 stress components are converted into 6 independent stress components. That is what we learned. Right? Now, so like this, if you want to represent a matrix consisting of sigma 1, sigma 2 and sigma 3, how you write? You know that sigma 1, sigma 2 and sigma 3 are only normal stresses. They are the normal stresses, they are the principal stresses. In this matrix, where are the normal stresses? Sigma xx, sigma yy and sigma z. These are the normal stresses. This is the reason why for a 3-dimensional state of stress with principal stresses acting in their respective principal directions, you can write matrix like this: sigma 1, sigma 2 and sigma 3. They are the normal stresses. Principal stresses are the normal stresses. They are only normal because principal plane does not carry any shear stress. You can say principal plane is the shearless plane. Understand? Therefore, what are the shear stresses? 0 simply. That is the reason why I can write elements in other locations 0. So this is how we represent the stress matrix for the 3 principal stresses: sigma 1, sigma 2 and sigma. Like this. Okay? Now I define the stress invariance. I say I1 is the first invariant. I define this I1 as sigma 1 plus sigma 2 plus sigma 3. This is how we define. Okay? So why we define, we have to go back into details. Then we understand everything. So here I hope it is not necessary. Define I1 as sigma 1 plus sigma 2 plus sigma 3. Next, I2 second stress invariant is equals to determinant of sigma 1 0 0 sigma 2 plus determinant of sigma 2 0 0 sigma 3 plus determinant of sigma 1 0 0 sigma 3. This is how I define the second invariant of stress. You can say stress invariant also. Nextly, third stress invariant, determinant of sigma 1 0 0 in first row, 0 sigma 2 0 in second row, 0 0 sigma 3 in third row. When you evaluate this determinant, you get like this: sigma 1, sigma 2, sigma 3. Similarly, if you want to evaluate I2, you can evaluate. How you can evaluate I2 equal to, determinant of, say A, B, C, D. Determinant of, if you write A, B, C, D. This is determinant. Determinant of A, B, C, D. Tell me what it is: simply AD minus BC. This is the well-known formula. That is the reason why I2, if you determine, how you get I2 equal to sigma 1, sigma 2 minus 0 into 0. You get simply sigma 1, sigma. I2 equals sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma 1, sigma 3 you get. If you evaluate I2, you get as sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma 1, sigma 3. That is how you get I2. And we have I3 here. Okay. Let us see how they are helpful. Now, I take the von Mises stress, sigma Vm. We have the expression here. Von Mises stress. Now, von Mises stress equals to 1 by square root of 2 into square root of so and so. Yeah. This I expand. Okay. So how you expand? This is in the form of A minus B whole square. So therefore you can expand. Sigma 1 square plus sigma 2 square minus 2 into sigma 1 sigma 2. Similarly, this also can expand, this also can expand, and write as 1 minus stress equals to 1 by square root of 2 into sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2 plus sigma 2 square plus sigma 3 square minus 2 sigma 2 sigma 3 plus sigma 3 square plus sigma 1 square minus 2 sigma 1 sigma 3 to the power of 1 by 2. This is how we write. After expanding, you get like this. Now, we simplify. 1 minus stress equals to 1 by square root of 2 into. Now, say here, sigma 1 square plus sigma 1 square. So, 2 sigma 1 square plus similarly, sigma 2 square plus sigma 2 square. 2 sigma 2 square. Sigma 3 square plus sigma 3 square. 2 sigma 3 square. Next. Minus 2 sigma 1 sigma 2 minus 2 sigma 2 sigma 3 minus 2 sigma 1 sigma 3. Go to the power of 1 by 2. Okay. Now, what I do is, I take this 2 common. When it comes out, because of this 1 by 2, it becomes square root of 2. Therefore, it lies outside as in the numerator, square root of 2. 1 minus stress equals to square root of 2 by square root of 2 into, because 2 has come out, sigma 1 square plus sigma 2 square plus sigma 3 square. Okay? And what remains here? Minus sigma 1 sigma 2, I write here, minus sigma 1 sigma 2 minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 1 sigma 3. You get like this. Okay? But here it is not appearing like this. In place of this, what we have in this expression, this. This replaces this. Let us see. 2 sigma 1 sigma 2 minus 3 sigma 1 sigma 2. How much you get? Minus sigma 1 sigma 2. So there is no change. Plus 2 sigma 2 sigma 3 minus 3 sigma 2 sigma 3. You get minus 2 sigma 3 sigma 2 sigma 3. No change. Next. Plus 2 sigma 1 sigma 3 minus 3 sigma 1 sigma 3. You get minus sigma 1 sigma 3. There is no change. So there is no change. Therefore, in place of this, I write like this. What for that we see? 1 minus stress equals to, see here, root 2 by root 2. Both will get cancelled with each other. You get 1 as the quotient. Now, square root of, now see here, sigma 1 square plus sigma 2 square plus sigma 3 square plus 2 sigma 1 sigma 2 plus 2 sigma 2 sigma 3 plus 2 sigma 1 sigma 3. In place of this, what I can write? Sigma 1 plus sigma 2 plus sigma 3 whole square. And what is remaining here? Minus 3 into sigma 1 sigma 2 minus 3 into sigma 2 sigma 3 minus 3 into sigma 1 sigma. So when 3 comes out, when minus 3 comes out, minus 3 into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. This we rewrite as sigma Vm 1 minus stress equals to square root of, what is sigma 1 plus sigma 2 sigma 3? I said stress invariant I1. First stress invariant I1 square. So minus 3 into, what is sigma 1 sigma 2 sigma 2 sigma 3 plus sigma 1 sigma 3? It is the second invariant of stress I2. So therefore, 1 minus stress we can simply represent in this form. So 1 minus stress equals square root of I1 square minus 3 into I2. Understand? No. Again, as I said, for design criterion, 1 minus stress should be less than or equal to sigma. Okay. Now we shall see for plane stress case. For plane stress case, as I said, sigma z equals to 0, tau zx equal to 0, tau yz equals to 0, and epsilon zz is not equal to 0. Only in plane strains are non-zero. In plane stresses are non-zero. What are the in-plane stresses? They are sigma xx, sigma y and tau x. They are non for plane stress case. Hence, first stress invariant I1, it appears like this, sigma x plus sigma. Okay, right. Next one. I2, how you get? I2 equals sigma x, sigma y minus tau xy square. Okay. Next, I3, you get 0. I3, you get 0. Because I tell you here, observe carefully. What is I1? Sigma 1 plus sigma 2 plus sigma 3. For plane stress case, sigma z is 0. Tau zx is 0. Tau zy is 0. Understand? Only in plane stresses are not here. Right? So I1, I2 and I3 you get. I3 you get 0 for plane stress case. I1 is sigma x plus sigma y and I3 is sigma x, sigma y minus tau xy square. Right? Now we shall see the plane strain case. For plane strain case, in-plane strains are non-zero. The strains out of plane are zeros. And moreover, sigma z is not equal to 0. You know this. Hence you get the stress invariance like this. I1 equals to sigma x plus sigma y plus sigma z. And I2 equal to sigma x, sigma y plus sigma y, sigma z plus sigma z, sigma x minus tau xy square. Here, sigma z is appearing because sigma z is not equal to 0. Therefore, it is appearing here. Understand carefully. In plane strain. Okay? So, where sigma z equals nu into sigma x plus sigma y. Therefore, sigma z is not equal to 0. Okay, this is what about the von Mises stress. Right? Okay. Dear students, now we shall enter into second chapter. It's a unit number 2. What we learn in unit number 2, in fact, finite element modeling, the discretization of the domain. Next, element numbering, node numbering, shape functions, preparing element properties, then preparing global properties, then applying boundary conditions, then solving the obtained set of equations for this solution. All these we learn in unit number 2. But to discretize the domain, what type of element we use? There are several types of elements. That is the reason why firstly we see discretization of domain. Discretization of domain. Using the basic idea of the finite element method, we discretize an irregular domain into many subdomains. What is subdomain? Subdomain is a finite element. The size of each subdomain is very small. An irregular domain we discretize into many small subdomains. Subdomain is the finite. This is simply equivalent to replacing the irregular domain having infinite number of degrees of freedom into finite number of degrees of freedom. Finite number of degrees of freedom. There are different methods of dividing domain into subdomains. For problems involving complex geometries, finite element discretization is based on manual procedures. Manual procedures. However, some automatic mesh generation techniques have been developed for the efficient idealization of complex domains. How you idealize the complex domain? A question comes into mind. Selecting an element. Domains may appear with 3 dimensions, 2 dimensions and 1 dimension. So therefore, what type of element we choose to discretize a domain? What are the basic shapes of the elements? All these questions come into mind. That is the reason why we shall see now the basic element shapes. Okay? Now, choosing the shapes, sizes and number of elements carefully is the primary step to simulate the body without increasing the computational effort. When you increase the number of elements, what happens? The computation time increases. Another constraint. And the computers also require more storage capacity. That is the problem. So therefore, as an engineer, you have to work with fewer elements for more accurate solution. You have to work with fewer elements. When you take a complicated structure such as an aircraft structures, how many elements, you can consider millions of elements. Very complex domain it is. When you discretize the body of the aircraft structure into subdomains, millions of subdomains we observe. You have to solve such a problem, with the aid of computer. So computer also requires more memory, storage problems will arise. That is the reason why the engineers, look for reducing the number of finite elements. They would like to work with fewer elements. Okay. So choosing the shapes, sizes and number of elements is carefully the primary step to simulate the body without increasing the computational effort. So domains will appear with 3 dimensions, 2 dimensions and 1 dimension. Firstly, we shall see one-dimensional elements for idealization of one-dimensional domain. One-dimensional domain. So when do you consider the one-dimensional elements? When the geometry, material properties and field variables are completely dependent on single variable. You can choose the one-dimensional element when the material properties, geometry and the field variable are completely dependent on one variable. I explain. Take me an example. Now, let us take a bar of uniform cross section. Let us take a bar of uniform cross section. This is a bar of uniform cross section. One end of the bar is fixed. This bar is under the action of a pull, say P. L is length of the bar. Before applying this load P, mark a point here on the surface of the bar. Apply the load P. When you apply the load P, deformation takes place. Deformation appears here as elongation. Under the action of force P, length of the bar increases. Therefore, this point tends to move in the direction of force P. This point tends to move in the direction of force P. Now, how many displacements this point has? Only one displacement. Only one displacement. Okay. So displacement is the field variable which is simply dependent on the variable x. If you consider a reference frame like this, x-axis I take like this, and y-axis I take like this, and z-axis is perpendicular to the planar board. Here the displacement of this point is dependent on the variable x only. The displacement is dependent on the other two. The displacement is dependent on the variable x only, and it is independent of the other two variables y and z. The displacement is dependent on the variable x only, and it is independent of the other two variables y and z. Therefore, I can consider this domain as one-dimensional domain. What the domain represents here? Simply the body of the bar. It is a bar having uniform cross-section. Cross-section is same everywhere. So cross-section is constant because it is same everywhere throughout the length. You can consider it constant. Cross-section area is constant. What is variable here? Only length. If you consider only this part, this is the length. If you consider only this part, this is the length. So length is variable. So x is the variable here. Right? The material properties depend on the variable x. The displacement of this point depend on the variable x. And the geometry of this body depends on the variable x. Therefore, I can consider this as one-dimensional problem. For finite element idealization of this body, or you can say domain, you can take one-dimensional element. One-dimensional element consists of two nodes. I said, what is node? Node is represented by a discrete point where the field variable is unknown. Node is represented by element corner. Element corner represents the node of the element, finite element. Node is a discrete point. In this case, node is simply the end point of the element here in this case. Okay? How many nodes it has? Two nodes it has. For one-dimensional problem you can use. What type of problem? A body under pull or push. A body under pull or push. For this kind of problems, you can use one-dimensional element. One-dimensional element. How many nodes it has? Two nodes. And each node has only 1 degree of freedom. Therefore, how many degrees of freedom are there in this element? 2 degrees of freedom. You can also say it is a two-noded one-dimensional element with 1 degree of freedom at each node. Because it is the elasticity problem, if you discretize this domain into 3 subdomains, okay, this is represented by a one-dimensional element with how many nodes here? 2 nodes. And this element consists of 2 nodes. This is the reason why. If you say this is first element and this is second element, the second node of the first element coincides with the first node of the second element. First node of the second element is this, second node of the first element. These two will coincide here. This is one element with two nodes. This is another element with two nodes. These two nodes will coincide with each other here like this. So how many elements are there? 3 elements are there. 3 one-dimensional elements. How many nodes you can consider? 1, 2, 3, 4. 4 nodes you can consider in this cell. Right? Therefore you can say it is a 3-element finite element model. It is a finite element with 3 elements. How many nodes are there? 4 nodes. Okay, and each node has only 1 degree of freedom. To solve the problems of this type, you can consider one-dimensional element. You can say one-dimensional bar element also. Some people say truss element. Some people say truss element. One-dimensional truss element. Okay, it is a one-dimensional truss element having 2 degrees of freedom with 1 degree of freedom at each node. So that is what we see here. This is a one-dimensional element. It has 2 nodes. It connects 2 nodes. Node 1, node 2. First node, second node. Each node has 1 degree of freedom. And this degree of freedom represents translation. Each node has 1 translation. To what type of problems you can use this type of element? A bar under tension or a bar under compression. Okay? Let us stop here. Thank you very much.